All right, so I'd like to talk about carbocation rearrangements in organic chemistry. So of course, carbocation, that is just a carbon with a positive charge. Cation means a positively charged ion. And so when you're doing organic chemistry mechanisms, if you run into a carbon with a positive charge, it can rearrange if it can form something that's more stable. So our general rules, things to look for are the more substituted it is, the more carbons there are around that carbon with the positive charge, the more stable it's going to be. So with 3 methyl groups around, that's better than 2, better than 1, right? So primary carbocation, secondary, tertiary, right? As it goes down, it becomes less and less stable. The least stable one is just 1 carbon, just the methyl cation. It can also rearrange and become more stable based on other factors like resonance nearby. So this ring structure, even though this is secondary and this is secondary, this rearrangement would be favorable from one to the other because now it's stabilized by the resonance of that pi electron that's there. The pi bond will make a big difference. So that's things to look out for in general. So basically, if it can rearrange, it will, right? And I'll go through some examples of showing how the mechanisms work for that. So common mechanisms that you might have to look out for, something like an SN1 or an E1 or an addition to an alkene. Right? Those all have potential for carbocations and rearrangements. So if our first bond breaks, say it's an SN1 overall, we're not going to do the whole mechanism. Right, so if this bond breaks, that leaves us with a carbocation, and then we got to stop and think, okay, can this rearrange? And so how we do that is we think, here's the carbon with the plus charge, right? Would the carbocation be better 1 carbon over to the left, or would it be better 1 carbon over to the right? Right, so in this case, to the left, that's a primary carbon, that's going to be less stable. To the right, that's more substituted tertiary, that's going to be more stable, so it'll rearrange to this spot here. How do we do that? So given our drawing, this carbon has a methyl, and this carbon over in the end. So there's 1 hydrogen remaining here that was undrawn in the skeletal structure, and we can use that for the rearrangement. And so what happens is the electrons shift over 1. So the arrow starts in the middle of the bond, points to the carbon with the positive charge. Our hydrogen is slid over to this, leaving the positive charge on the more stable spot. So this is our rearrangement. That's called a hydride shift. And if there's a hydrogen in that more stable spot, that's what's preferentially going to happen. I'll show you a different example. All right, we'll do our first SN1 or E1 step here. Right, so our positive charge is up here, and we got to stop and think again. It's best to be methodical about this if you can. Is it going to be more stable in this position? Right, it should be about the same. Right, so from secondary to secondary, no difference. Would it be more stable in this position? Yeah, there's more carbons around to donate electron density, so that's going to be a more favorable spot. 1, 2, 3, 4 bonds to this carbon, though. There's no hydrogens available. In that case, a methyl shift is possible. Just going to write in my CH3 there. And the arrows are essentially the same. So up here, from the middle of the bond, moved over, same thing. In this case, I've actually changed the carbon skeleton, though. Right, so ring's the same. This one group hasn't moved. This CH3 group has moved over 1. That's going to replace the positive charge over here. So now I am in a more favorable position than it was before. So that's a good rearrangement. That's a methyl shift. Name makes sense in this case. So if we're looking over here, our positive charge, I've got a bunch of branching over here on this end. Right, so if our positive charge was over here, this would be more stable, but it can only rearrange nearby. So our only two options are here and here. So in this case, that would be moving a positive charge to a primary position, which is less favorable. In this case, that's moving the positive charge to a secondary, and those are equal. So it would not rearrange. So it just doesn't change at all in that case.